So let's go to in-class activity 3. In-class. Now here's the thing. Since I'm not using that mic, I think I can now take this away and show the dot cam. Yeah, because I think I only had to have this up for the dot cam. So here, let's do this here so you can see it on both sides. Now here's the thing. Do we know if Evan's happy? Evan, can you still see the dot cam?
Yeah, it's good.
And you can still hear me?
Yeah.
Okay, all right, so we're good. All right, so now this problem here, where we had gotten to is that the power for the 1 kilo ohm resistor was 58 milliwatts. And we talked about the fact that these are 25 milliwatt rated resistors. So anything over 25 milliwatts could not be used in this design. Otherwise, it's going to start to turn black and smoke because I've now dissipated more power than that resistor was rated for. So the last thing we need to do is we need to find the power for these 1, 2, 3, 4 remaining resistors. At some point, I'm going to put this recording online as well. So since I have to record it anyway, you can go back and watch it later. Okay, so let's find some of the other powers. So I now know that the voltage right here is 12.4 volts. I can find the current by taking 12.4 and dividing it by 1 plus 1.364, and that will give me the current down through here, and then I can use I squared R to find the power for that side. Okay, so I'm going to write over here because I'm out of room. What I'm saying is that if that node is 12.4 volts, I now have these resistors over here. There's some other stuff over here, but I don't care about it. Right? But I do know that this is 1 kilo ohm, and this is 1.364 kilo ohms, and this is 2.2 kilo ohms, and this is 3 kilo ohms. So if I can find the current down the left branch and the current down the right branch, I can then use those currents to find the power. So if I call the current down the left branch I1, then I1 is equal to 12.4 divided by 1K plus 1.364K. The voltage across those two series resistors divided by the resistance is the current. That's Ohm's law. I equals V over R. So that current is, let me find the page. Well, great, I didn't write it down. So I need somebody to get out their handy dandy calculator and tell me what I1 is. That's the thing, there's so many ways to solve these problems and I don't do the same way every time, so I don't have the answer. What's your name? Riley! I have 2 Rileys this quarter. Do you know the female Riley? No. Okay, Riley, what's I1? 5.08 milliamps. Okay, so that means the power for the 1K should be 5.08 milli squared times the resistance. That's I squared R. The power for the 1K is 5.08 milli squared times 1K. That's I squared R. And so I got that the power for the 1K was 27.5 milliwatts. 27.5 milliwatts. So that one is also out of spec because it's a little bit bigger than 25 milliwatts. Questions? Yes, talk to me. $1,364. It is $1,364. That's what it is. 1.364. That's right. So this is 1,000 plus 1364. 1,000 plus 1364, so 12.4 divided by 2,364. All right, 12.4. I very rarely write numbers like this, by the way. We use kilars, millis, gigas, nanos, micros. But yes, okay. So it's 12 divided by 2364. 12.4 divided by 2364. Okay, you good? All right. So the power for 1364, or the 1.364K, would be 5.08 milli times 1.364K. And that 5.08 milli is squared. 5.08 milli squared times 1.364K. And I got that one, it has the same current. So that one is, I think 37.5. 37.5 milliwatts. So far, none of our resistors are in spec. So you just got to use higher rated resistors for this circuit. 37.5 milliwatts. Questions? What do you think I'm going to do next? What am I going to do next? Yes. Find the current for the other side. So I2 is going to equal 12.4 divided by 2.2K plus 3K. That's 5.2K. 12.4 divided by 5.2K. $12.4 divided by 5.2K, what's that current? Milliamps, 2.38 milliamps? Okay. I think you guys get it. I'm just going to give you the next two answers so we can move on. So the power for the 2.2K, and you can check this during your study time, because I know you all have private study time with circuits. The power for the 2.2K is 12.3 milliwatts. So that one is actually okay. And the power for the 3K is 17 milliwatts, 17.1 milliwatts, okay? So the only two resistors that are okay are those two on that right branch. They're both below 25 milliwatts, so they're within spec. Questions? I went through all that trouble learning how to use that mic, and it don't work. Ain't that about a blip? Okay, never mind. Can the back row hear me okay? Okay. All right. I'm going to do another problem. So far, every problem we have done has been balanced. I've had a balanced bridge. What was the definition of a balanced bridge? How do I know the bridge is balanced? There's no current through the detector, and there's another way I know it's balanced. What's the other way? The diagonal resistor product, right? So in other words, there's no current through the detector means it's balanced. And also, if 1K times 3K equals 1.5K times 2.2K, I know it's balanced. Those are the two ways I know it's balanced. So is this bridge balanced? No, because the product of these two resistors does not equal the product of those two. It's not balanced because 1K times 3K does not equal 1.5K times 2.2K. So because it's not balanced, that means that the current through that detector is not equal to 0 amps. It's not balanced, which means the current through the detector is not equal to 0 amps. So that ammeter, remember the detector is just an ammeter. This is an ammeter, which now everybody has had labs, so everybody knows what an ammeter is. All right, woohoo! So when it asks me to find the current through that detector, I got to figure out a way to do that. Well, we know KCL, we know KVL, And we know some other things. So what it says here is that if the voltage drop across the detector is negligible, negligible we take to mean 0. Okay? And we'd already talked about that negligible means 0, and a negligible voltage drop we're calling 0. So 0 volts means short circuit. And it also means 0 ohms. Negligible voltage means it's so small you can just call it 0. So the way we can model the ammeter is just make it 0 ohms. This is a question I got in lab yesterday. When you put the wire on the circuit, why didn't you just get the same thing you did with the ammeter? It's because an ideal ammeter would have 0 ohms and 0 volts, but your ammeter was not ideal. And depending upon the setting on it, you were getting somewhere between 0.1 ohms and 100 ohms. Right? So unless it's acting exactly like a wire, you're not going to get exactly what you get when you put it across a resistor. But you are on some level shorting out the resistor, which is why we don't put ammeters across devices to measure current. We put it in series with devices. Questions? So I'm going to redraw this. And I have 20 volts, 1 kilo ohm. And now I'm going to replace the ammeter with my negligible voltage, which is going to be a wire. And there is current through this wire, but I'll worry about that in a minute. I want to simplify this in order to solve the problem. I'm replacing the ammeter with a wire to represent negligible voltage and 0 ohms. And I'm going to simplify this to solve it, and then at some point I will come back and find the current through here, which is the answer to the question. What's special about the 1.5K and 3K resistor? What's special, Mark?
1.5K is a half of.
It's a what?
It's half the resistance.
Yeah, but that ain't special. That don't make them cute. You wouldn't ask for the phone number because of that. Yes, Ryan. They're in parallel. You're right, but I care more about them being in parallel. Okay, so 1.5K is in parallel with 3K. And 1K is in parallel with 2.2K. So I can redraw this like this. I'm down to 3 resistors. The top one is still 1 kilo ohm. This top right one is now 1K in parallel with 2.2K. 1K in parallel with 2.2K is 687.5 ohms. $1.5K in parallel with 3K is 1 kilo ohm. Let's stop here for a minute. Are there any questions? Yes, talk to me.
So after you combine the parallel ones, why do they become series after that?
Well, think about it like I'm squeezing these two together, right? So this is all one node, that's all one node. So when I put them in parallel, these are squeezed together down here. And when I put these two in parallel, they're squeezed together up there. And since they share that one node, they're in series. Because when 2 elements meet at a node, they're in series. Okay? Other questions? All right, so now we have one more step before we can answer the question. I need to find the voltage across that 1K resistor, and I also need to find the voltage across that 687.5 ohm resistor. What does this look like to you? What do you think I'm going to do? What little ditty have you learned earlier this week or last week that you think I'm going to use to find those two values? I've got series resistors and a voltage that divides across them, and I don't want to do KVL. What am I going to do to find those two voltages? Voltage divider, voltage divider. So the voltage for the 1K is 1K divided by 1K plus 1K plus 0.6875K times 20. The voltage for the 1K using the voltage divider is the 1 kilo ohm resistor. Notice there's two of them, but it doesn't matter. They're going to have the same voltage drop anyway because they're the same resistance. It's 1K plus 0.6875K times 20. So the voltage across the 1 kilo ohm is 7.441 volts. I'm sorry? Voltage divider, voltage divider, voltage divider. That's the voltage divider. And there's two of them. So that means the voltage drop across here is 7.441 volts. The voltage drop across here is 7.441 volts. 7.441 here, 7.441 here. And because the sum of the voltages around the loop's got to add to 0, that's KVL, I know the voltage across the 687.5. So the voltage across the 687.5 is 20 minus 2 times 7.441. 20 minus 2 times 7.441. Why did I do 2 times 7.441? Because there's two 1K resistors. That's right, because there's two 1K resistors. And that voltage is 5.116 volts. Okay, question? I do. When this gets ugly like this, if I ever ask you to check it with KVL, if you could do at least 3 decimals, you're more likely to get something closer to 0. It's not going to be exactly 0 because we're rounding all over the place. But 3 may be better than 2. On a test, I don't even know if I tell you, to be honest. All right, so now we're ready to answer the question. I've got a resistor here. I've got a resistor here, and I have ID coming out there. Okay, so I need to find the current down through the 1K resistor, and I need to find the current down through the 1.5 kilo ohm resistor. So what you do here is, I know that the voltage drop across here is 5.116. So the current is 5.116 divided by 1K. And I know that the voltage drop across that bottom one is 7.441. So the current right here should be 7.441 divided by 1.5K. So the current down here is 5.116 divided by 1K. The current down here is 7.441 divided by 1.5K. I want you all to use KCL to find ID. Tell me your name, please.
Aaron.
Aaron.
Is the reason you're making that simplification because the one is in parallel with 2.2, they share the same voltage?
They do have the same voltage,
So
and if I want the current at this node, I either need to do KCL on the left side or on the right side. So I have to go back. It doesn't matter. I better get the same answer either way, but I got to split them back apart.
Okay.
Right? So I need to find the current through the 1K and the current through the 1.5K. Alternately, you could do the current through the 2.2K and the current through the 3K, but you get the same answer either way.
Okay.
So once somebody tells me what ID is, we're done. What is ID? 0.015 milliamps. You're right, but you're off by a multiplier. I got,
Maybe I misread the website.
yeah, I got 0.156 milliamps. So you're off by a multiple of 10. Or 156 microamps. 0.156 milliamps or 156 microamps. Yeah, so you lost a zero somewhere. Or you added a zero somewhere. So, okay. Questions? Any questions? Going once? Aaron? Aaron is squinting.
So you find the two currents above and below.
Yeah.
How do you know what, oh, is it the top minus the bottom? How do you know?
Okay, so think about N equals out, right? Wait a minute, why do I still have this on? Think about N equals out. So yes, so the current coming into the node equals ID plus the current going out through the 1.5K. So current in equals current out. Here, I'll write it up here. I'm out of room, but I gotta stay on here because E can't see it if I come off of here. So ID equals the current through the 1K minus the current through the 1.5K. Right? Current in equals current out.
Thank you.
You're welcome. Okay, so now we're going to do one more before we move on to delta Y equivalence. So even though I have not shown these leaning like the diamond, this is still a bridge, okay? Now assume that instead of putting an ammeter between my bridge, I put a voltmeter. That's what that V naught represents. That's now a voltmeter instead of an ammeter. Is this bridge balanced or not? And how do I know? Is that bridge balanced? No, the bridge is not balanced, okay? It's not balanced because 24K times 20K does not equal 33K times 36K. So if I had shown the current would not equal 0. And also, which I think I told you when we first introduced this, that voltage would not be 0 either. So neither one is 0. That's by definition of balance. The current would be 0 and the voltage at that point would be 0. Okay. I want to know what V naught is, and I'm going to use the voltage divider. Remember, we model, just like we model an ammeter as a short circuit, 0 ohms, we model a voltmeter as infinite resistance open circuit, right? So I've already drawn it here for you, but we would model a voltmeter as infinite resistance open circuit. So I've actually already done that for you. So by showing that break there, I'm saying there's no current flowing, it's infinite resistance. And now what's special going on with the 24K and the 33K? They're in these two. Series, but if I put these two together and put those two together, the result's in parallel, but these are in series. That means they have the same current. So what that means is that this 24K and this 33K actually divide that 15 volts. And I can call that VA, the voltage at node A. And this 36K and this 20K also divide that 15 volts. And I can call that the voltage at B. Yes?
So that, you get that from KVL.
I could, yes. I could also do that with KVL. Right?
If they're connected, or are they not?
They are connected in the middle, and that's what series means. When exactly two things meet at a node.
I thought that
It's a voltmeter. That's not a connection point of any circuit element.
Okay.
That's just me putting a voltmeter right here to measure the voltage.
Okay.
And it's modeled as infinity, so even if I did model it as a resistor, it's open. It's an open circuit. Aaron?
On a test, will you want us to say, like, I'm applying KVL to each
No,
resistor?
if I don't tell you, you just do it. And I should understand it unless it's gibberish. Okay? But a lot of times on the test, I will tell you because I'm testing your understanding of something. So I might say, do the voltage divider to solve this. Do the current divider to solve this. And I'm explicit about what I want you to do. And at that point, you can use other stuff to check it, but I need you to do the voltage divider because I want to make sure you understand the voltage divider. Okay? So we're going to do the voltage divider to solve this one. So that means that VA is the voltage across the 33 kilo ohm resistor. So that's 33 over 33 plus 24 times 15. VB is the voltage across the 20 kilo ohm resistor. So that's 20 over 36 plus 20 times 15. So let's talk about the common mistakes students make when they do this problem. If I tell them to find VA, they don't know if the 24 or the 33 should be in the numerator. If I ask them to find VB, they don't know if the 36 or the 20 should be in the numerator. Ryan.
Aren't those two resistors
What's in parallel?
in the 33?
Oh.
Kayla? Kayla's gonna answer that question.
Kaylee, but no.
Dang, you're Kaylee. Who is Kayla? You're Kayla. Good Lord. I'm dying. I'm sorry. No, I'm not dying. Let me not say that. No, I don't want to die. It's Kaylee. Kaylee. Where are they not in parallel? I don't even know no more. I lost it after I found out you weren't Kayla.
Because they're in series.
They're not parallel because they're in series. That's an awesome answer. Okay, so 24 and 33 kilo ohm are in series because they meet at that node. Two elements that meet at a node. The only way these two would be in parallel is if there was a node right here in the middle, Ryan, and there's not. There's a voltmeter right there with the infinite resistance. Kaylee. Okay, so let's talk about why the 33 is in the numerator, because this is the thing students miss all the time. Voltage is always with respect to ground. Node voltage is with respect to ground. This node at the top has a value of 15 volts. So you would never put the 24 kilo ohm in the numerator because that would be finding that voltage with respect to 15 volts. So if I tell you to find the voltage at node A, you need to find the voltage at node A with respect to my reference, which is ground. And when I do that, that's the same as the voltage across the 33 kilo ohm. Everybody see that? Or the voltage at node B with respect to ground is the voltage across the 20 kilo ohm. That's how you know which resistor is on top. Yes. You don't understand any of that. I don't understand the words that are coming out of your mouth. Okay. So when you're looking for a node voltage, you guys also did this in lab yesterday. You always put the black to ground. And then you touch one of the nodes, and that's the node voltage with respect to ground. This is the part of the lab where they talked about elevation, and I don't even remember what the other word was because I don't use elevation, but elevation and steeple? Sinking? I don't know. So it's always with respect to ground though. So if I'm finding the voltage with respect to ground, this is where you put the red and black leads of your voltmeter. That just so happens to be the same spot as the 33 kilo ohm resistor. So if I find the voltage across the 33 kilo ohm, that's VA. It's because I put ground at the bottom of the circuit. This is because this is my reference point.
At the top, it hasn't like gone through yet. So like that's why
It's because I don't measure voltage with respect to 15 volts. I measure voltage with respect to ground. That's my reference, right? You pick a standard, right? I always use the bottom. I don't have to. I can make ground the top of the circuit, and then that means the voltage down here is negative 15 volts. It still won't change the VA, right? Because when I do the calculation, the number for VA is still going to be the same. It'll just be with respect to negative 15 volts.
Have to go back in current, let's go back in.
No, it's because I made it the reference point, which I always make it the bottom of the circuit. I don't have to. I can make that top node ground as well, right? And then it changes your answers, but the delta for the voltage is still the same, right? I'm looking for the difference between the potential here and the potential here. Even if I put ground up here, that delta would still be the same. I don't want to do that though. I'm consistent and I always put ground at the bottom of the circuit. But you don't have to do that. You can put ground on any node. But when you're looking for a node voltage, it has to be with respect to somewhere because it's a polarity. And I always, this is the standard, is with respect to ground. You don't find voltage with respect to a 15 volt node. Does that make sense? Kind of. Okay. Let that marinate for a minute. Okay. So this voltage has no meaning if I don't have a reference. So I have a polarity. Where am I going to put the plus? Where am I going to put the minus? I put it at ground. Same over here. Polarity. I got to have a voltage with respect to somewhere. And I put the minus at ground. Right? So that makes this voltage across the 20 and this voltage across the 33. What are those values? What's the voltage A? 8.68 volts. Okay. And what's the voltage B? .36 volts. Okay. So what you would find, tell me your name. In the back. Josh. What you would find is that if I had used the 24, the answer I would get is 15 minus that number. Or if I use the 36, the answer I would get is 15 minus that number. And I do have the voltage across the 36 kilo ohm resistor, but that's not the voltage at node A. That's the voltage at this element here. Remember, there's two kinds of voltages: node voltage, element voltage. Node voltage is at a node with respect to ground. Because of where the battery's connected. The battery is positive on top, negative on the bottom. Yeah, but guess what? Even if the battery was upside down, I would still do that. But we know current's flowing that way, right? Because this thing's delivering the power. So the current's coming out and going down through that resistor and down through that resistor. Right? Okay, that's actually it for Wye-Delta. So before I talk about this Wye-Delta, that's it for Wheatstone Bridges. I'm about to talk about Delta Y, but are there any questions before I do that? Oh, I didn't tell you the answer. What's V0? How do I find V0? I found VA and VB, but how do I find V0? It's VA minus VB. Okay, here's the question for you. Why isn't it VB minus VA? Because of the polarities on V0. Higher potential to lower potential, VA minus VB. If I flip-flop the plus and the minus, it would be VB minus VA. You have to look at where the plus and the minus are. This would be the red and black on your voltmeter. If you flip that on your voltmeter, you get a negative number. So what is V0? .33 volts. So I think what I'm going to do is I'm going to stop the exam here, okay? And I will put the rest of this on exam 2. You want to calculate the current? The current's actually easy. Let's do that. Let me tell you why the current is easy. Because this 15 volts is across these two, the current right here, let me write at the top. The current right here is 15 divided by 2.24 plus 33K. right? And then the current over here is 15 divided by 36 plus 20K. And then if I do those two currents and I add them together, that gives me the current from the source, which is the current through the 15-volt source. Okay, so what is the current? The current in the middle. Well, I can't calculate this time because I didn't tell you about negligible ammeter resistance. I didn't even put an ammeter in there, right? I just have that voltmeter there, which we're modeling as infinite resistance. But you could do that, right? I would then have to redo all of this because I have to put a wire there to model that as a short, which means nothing we have here I can use. Other questions? Okay. So the other thing that is related to this, but I'll put this on midterm 2 because I don't want too much stuff on midterm 1, is how do you simplify these circuits with these deltas and these resistors in the middle? Mason came and asked me this today. Where's Mason? Where's Mason? Okay, so there's a homework question that asks you to find R. And R is like on one of the branches, but you don't know how to do that. So until you learn about delta and Y equivalents, the only way to do those problems is to write 3 KVL equations and then solve for the unknowns. I'm going to show you another way to do that where you simplify the circuit and then solve for R. And that's called delta Y equivalents. So when you have a circuit that has other stuff over here, and these resistors are in a triangle like that, we call it a delta. A delta. It's also called a pi. A delta or a pi. And then if you have a circuit over here that may have some stuff there and there and there, but it has this configuration in the middle, it's called a Y. It's called a T or a Y. So now you have 3 kinds of configurations of resistors: series, parallel, delta, or Y. There is a way to convert between delta and Y to simplify the circuit, and that's what I'm going to show you now. One of them, and don't ask me how they figured out these formulas, I will give it to you on the test, so you ain't got to memorize, is if you have a Y and I want the delta, then it's the product of each of the resistors 2 at a time, divided by R1 for RA, divided by R2 for RB, and divided by R3 for RC. Okay? Or if you have a delta and you want to convert it to a Y, it's RB times RC over RA plus RB plus RC. The denominator is always the same, but the product of whichever 2 resistors you multiply is different. The way you do this is you superimpose these on top of each other and make sure when you do that calculation that R1 is there, R2 is there, and R3 is there. Or if I convert the other way, this is RC, RA, and RB. So as long as you're consistent with the nodes, you can convert from one to the other. Like I said, I give you the formula. You just have to be able to use it. You don't have to memorize. Questions so far? So here's what that superimposed looks like that I just mentioned. So this is when you convert from one to the other. There's ABC, R1, R2, and R3, RA, RB, and RC. There is a special, I didn't mean to do that. There's a special formula for this when they're all the same value. This is not the same balance that we just talked about. It's a different balance. And we say that the Y and delta are balanced. If all 3 resistors have the same numeric value, we say that the Y is balanced or the delta is balanced. And those formulas I just gave you simplify to either R delta over 3 or R delta equals 3 RY. That's just the algebra of those formulas I gave you. So we're going to do an example that's balanced first because it's easier before we do another one. So let's talk about what equivalent means. So when I tell you that this conversion is equivalent, that means that if I put a voltmeter or an ammeter at nodes A, B, or C, or an ohmmeter, they're going to read the same voltage, same current, same resistance, whether it has a Y or delta configuration. That's why this works. If I put a voltmeter, ammeter, or ohmmeter at any of those nodes, they read the same value, whether I have a Y or a delta. As long as all the connections outside of it are exactly the same, they will measure the same. That's why this works. That's why I can do that. Okay? It doesn't tell you anything about the inside. Once you get inside of there, the voltages may be different, the currents may be different, but as long as I'm measuring at those nodes, they have the same values. So now, you cannot say anything about the internal resistors and that they're not the same. That's what I was just telling you. This is where we're going to end class today. I have a network here, and all the resistors are the same. So they're all 30 ohms. I just didn't draw them all, right? That means it is balanced. I want to do deltas. How many deltas does that network have? Almost. 5. We're going the wrong way. Remember, I got to use the deltas to do a conversion. So you can't double count resistors. Every resistor can only be counted one time. So now it's 3. It's got to be 3 because I can only count each resistor one time. Because I'm about to convert them. So they can't be double counted. So there are 3 deltas. And since our delta is 30 ohms, I'm going to convert them to 3 Ys. So our Y is our delta over 3, which is 10 ohms because this is balanced. The 3 deltas are going to become 3 Ys. Each delta has a value of 30 ohms, and because they're balanced, our Y is our delta over 3. So when I redraw it, each Y is going to have a value of 10. So this is what it's going to look like. Here's my first Y, 1. Here's my next Y, 2. And then here's my last Y, 3. Okay, I'm circling the meeting point so you can see how this matches up. So if I gave these nodes names, this could be like C, D, E, F. C, D, E, F. Okay, so when you're looking for equivalent resistance, we have a dangling resistor. A dangling resistor is one where no current flows, so it does not impact the net resistance. Can anybody tell me where the dangling resistor is? The one at F, that's right. So when I look for the equivalent resistance, this dangling resistor has no effect on that answer. Because it's not in the loop and it wouldn't have current flowing through it if I put an ohmmeter across it, this resistor is now gone from the calculation. It's called a dangling resistor. Dangling resistor. You could actually finish this now without doing any more Y-delta conversions. Do you see that? If I take out that dangling resistor, now I'm going to have 1, 2, 3, 4 resistors in series. And over here, I'm going to have 2 resistors in series. And then when I put those together, they're in parallel. I want you to finish this network. Find the equivalent resistance between A and B, and that's where we're stopping today. Find the equivalent resistance between terminals A and B, and that's where we're going to stop today. Can I take this out? I don't think I can. Find the equivalent resistance between terminals A and B. You don't need to do any more Wye-Delta conversion. You can just use series and parallel to get the rest of them.